Welcome to another podcast. In this episode, we're going to be taking a look at our first compound interest example. For this example, I'm going to try to derive the compound interest formula by using an example with values in it so we can sort of relate where these values tie into the formula. So the example that I want to look at is, suppose that we deposit $1,000 for 2 years into an account paying 8% compounded quarterly. What compounding in this context means is compounding I want you to associate the term compounding with adding in the interest. So in other words, we're going to stick $1,000 into the account. We're going to let it sit there for 2 years. And then every quarter of a year, which would be every 3 months. So every 3 months, we're going to calculate the amount of interest we earned over that 3 months. And then we're going to put it back into the account, which means the account will be bigger every 3 months. It keeps getting bigger each quarter of the year. Now, we're going to calculate the interest using the only interest we know, which is simple interest. So for each quarter, I'm going to consider that to be a separate simple interest problem, which means that in order to complete this example, I'm going to have to solve 8 simple interest problems because I'm going to compound 4 times a year for 2 years, a total of 8 compounding periods. Now, I'm told that my interest rate is 8%. So the rate in the problem is 8% simple interest per quarter. So that's what I'm going to be taking a look at. Now, in order to do this, I kind of want to think of this as being maybe a timeline approach here, just to give you a little bit of an example of how this works. So I'm going to sort of consider this spectrum as the 2-year period over which the account exists. And so if I start with, time equal to 0 in the first year and time equal to 2 being at the end of the second year, we've got sort of our halfway point here after the first year. And then we start thinking about quarters. So first quarter, second quarter, third quarter, fourth quarter would be 1 year, fifth quarter, sixth quarter, seventh quarter, and then a total of 2 years. So I want to find the value of the account at each of those time intervals. We'll start with the first quarter. So our description here of what we begin with, we know that at time 0 we start with $1,000, and to figure out what our account size is at the end of the first quarter, the money sits in there for 3 months. It grows at a rate of 8%. Now that 8% is 8% per year, where simple interest is going to be calculated, but per quarter we add in the interest. Every quarter we come and add in the interest. Okay, so the way to do this using our simple interest formula is, remember that A equals P times 1 plus RT. And so for the first quarter, we would have A equals 1,000 times 1 plus 8%. Compounded quarterly would be 1/4. Remember that the T in the simple interest formula is the number of years. So if we're doing a quarter of a year in this first little bit, then T would be equal to 1/4. All right, if you just want to stick that in a calculator and get the answer here, it would be $1,020. So at the end of the first quarter, we have $1,020. All right, on to quarter 2. So I'll call this A1, we'll call this A2. So at the end of quarter 2, A2 would be, well, I begin that quarter with the 1,020 I had before, and I'm going to grow by the exact same amount, 8% for 1 quarter. And sticking that into a calculator, you will get $1,040 for that period. All right. Next up, it's 1,040 and 40 cents. Now, the reason I knew that something was up there is we had a bigger value, so we should have increased by a little bit more than we did in the first case. So in year 0, we had $1,000 to begin with, and you can see that we gained $20 over that period. So the $20 that we gained is the interest earned over the first quarter. The interest earned over the second quarter here is $20.40. In other words, it got slightly bigger. The reason it gets slightly bigger is I'm calculating the simple interest not on what I started with, but on what I ended with at the end of the first quarter. So that's going to be a recurring theme here. You're going to see that the interest we accumulate increases each and every quarter that we look at this. So similarly, for the third quarter, we would have $1,040.40. Applying the same growth rate here. And the result of that would be $1,061.21. So looking at the interest here, it would be a total of, let's see here, not quite $21. It looks like $20.81. So that's the interest earned over the third period. And then finally, the fourth period of that year, so let's see here, we've got 1,040.40, and then 1,061.21. And then at the end of the first year, we would start that fourth quarter with $1,061.21, applying the same simple interest rate for the quarter. And the result of that would be $1,082.43. So that's how much I would have at the end of the first year. Now we're going to have to repeat this process for the second year, but I want to do this in a smart way. In other words, I want to go straight from year one, and I want us to be able to figure out what we should have at the end of year two. So the end of year two would be if you're keeping track, would be A8. It would be the value of the account at the end of 8 quarters. And while I've been using the previous values this entire time, let's just look at what we've been doing. To get the next value in the sequence, I'm just taking the previous value and multiplying by this same value in the parentheses over and over and over again. That value in the parentheses is simply the growth rate. If you've watched the exponential model video, it's simply the growth rate that we are applying to the money each quarter. Now, if you take a look at what's going on, I'm going to have a certain amount of money that I started with. I started with $1,000 and A4. So let's talk about A4 first. All I did to get A4 was take the 1,000 I started with and multiply it by this growth rate 1, 2, 3, 4 times. So mathematically, we would use a power to represent that. That is going to be the exact same thing as that 1,082.43. So if you compare this with this, you're going to get the exact same value. This leads me to believe that I can find A8 by starting with 1,000 and applying that same rate 8 times because there are 8 quarters. And that is correct. I can do it that way. And if we were to do that, then what we would have here at the end of the next 4 years would be $1,171.66. Now, I want to sort of talk about the pieces that went into this, because the 1,000 here is pretty evident what it is, but I want to write the formula in sort of a different way here. And what I want to do is I want to somehow get the number of years into the problem, because as you look at the problem now, this 8 is the number of quarters, but what if we were doing this every month or doing it only once a year? The 8's kind of misleading. What isn't misleading, though, is we're doing it 4 times a year for 2 years. And so this formula is the one that I want us to kind of take a look at and see if we can't generalize. Okay, so if I'm trying to come up with a way of finding the future value of a compound interest problem, then the way to do that is you start with the amount invested, which is the principal amount. You multiply by 1 plus 0.08 is the rate for the problem. So the rate for the problem divided by 4. Now the purpose of 4 is it pertains to this quarterly term. So we give it the variable n, and I'll go back and talk about what n is here in a second. And notice it also appears here. It appeared in both places. And then the 2 is the number of years that I'm doing this process for. What we have at this point is the formula we were looking for. This is called the compound interest formula. Now, let's talk about the variables. We know what P is. We know what A is. R is the compounding rate. It's always given to you as an annual rate. So this is an 8%. This is an annual interest rate. So that's the percentage, but you write this as a decimal. So as a decimal. That's how you'll enter this in the formula. We're going to have some videos after this where we're going to look at plugging stuff into this formula. So take a look at those. N is called the number of compounding periods per year. And so just a quick glimpse at N, if I was compounding monthly, then that would say that N is 12. If I'm compounding daily, then N would be 365, or it could be 360, depending on what text you're looking at. 360 is the number of banking days, and so daily could be 365 or 360. You could look at hourly. You could compound the interest every hour. That would be 8760. Or you could look at it annually. Say you just want to add in the interest at the end of every year, then N would just be 1. Or it could be 4 like this example. But the point is, N measures the number of compounding periods per year, and T is the same as in the simple interest formula. T is always going to be in terms of years. And so you need to commit this formula to memory. But the one thing I don't want you to lose here is that the amount of interest that we're earning over each period is increasing the longer we go. That means that compound interest, this formula, exhibits the kind of growth we saw in the previous video that's a characteristic of exponential growth. And so this compound interest formula is an exponential growth model. And we're going to talk about the uses of that model in coming videos. All right, thank you for watching.